Hello everyone, my name is Andrew Kim and welcome to the very first video of the AP Physics C review session. Now, although it is an AP Physics C review session, I am going to only cover E&M simply because AP Physics C mechanics is not as hard as E&M, and way more people ask me help in E&M, and that's why I'm specifically making this video only for E&M. Now, if you feel like you still need help, then you have two options. First, you can watch AP Physics 1 videos because they're also about mechanics and they also cover enough basics and fundamentals that you need for AP Physics C test. Of course, you would have to try working on some harder application problems or some problems that involve calculus but except those special cases, AP Physics 1 video has good enough content, so you won't have to worry about it. Now, the second option is to come to Monday tutoring. If you come to Monday tutoring, then our physics ministers, Leo, Richard, and Kenny, and also the officers, me, Aiden, and people will help you. So those are two possibilities. So let's get started. Also, I forgot to mention this, but I am not going to run this review session. Now, the difference between this review session and the previous review sessions that the physics ministers has run is that this review session is more specialized for AP exam, meaning that I'm not going to follow the standard class or AP exam guideline, those units, but I'm going to make the videos based on my own structure. So this first unit will be lesson 1, electrostatics. So it's going to be in fact the same as unit 1 in our school, but starting from lesson 2, it might be kind of different from the schedule that the units that our school provides, simply because I feel like I can pace it faster. I feel like I can teach things in a more congested way. But anyways, let's get started. Lesson 1, electrostatics. So of course, we need to know Coulombs law. Coulombs law is that if you have two charges, Q1 and Q2, and if they are if they are distance, if the distance between the two charges is R, then basically there is a force, an electric force between the two charges, and that force can be calculated under the formula of K Q1 Q2 over R squared. Now, this formula makes so much sense simply because K is a constant, and Q1 and Q2 are literally the charges of the two charges. That sounds kind of weird. Charges of the two charges. But yeah, those are the two charges. Of course, if each charge is greater, then the force between the two would be greater because the charge is greater. If the charge is less, then of course the force between the two would be less. Let's think about an extreme case. What if the charge is 0? If the charge is 0, it basically means that they are not a charge. If they're not a charge, then there won't be Coulomb's law or Coulomb's force induced. Thus, no force, 0, which makes sense if you think about this equation, because if Q1 or Q2 is 0, then of course this formula would lead to F equals to 0. Now, if we think about R, or the distance between the two charges, of course, if the distance between the two charges increase, it means the two charges are getting farther apart. If the two charges are farther apart, it's going to be harder for the two charges to form force between. Thus, they will have less force induced by the two charges. That is why R is not going on the numerator, but going on the denominator, so that if R increased, then force decreased, and when R decreased, then force increased. Now, that being said, let's look at our second concept. Now, our second concept is electric field. And when I start explaining about this, a lot of people find this hard, unlike Coulomb's law. That's because basically Coulomb's law and electric force is, after all, a type of force. We've been looking at force in mechanics as well for a long time, so we're already familiar with what force means and how it works. But electric field, it's a field, and we've never talked about any type of field before. That is why people find it hard. Now, what electric field basically is the electric force that a unit charge feels. So when you have a charge, this time we're not talking about a pair of charge, we're not talking about two charges, but we're just talking about a singular charge. Now, if you have a singular charge, then this charge would make this electric field. It would make these arrows coming out from it. And what these arrows notify is that this arrow shows how charges, positive charges, would get force. Think about it. Let's say we put another positive charge over here. In which direction would it get force? It would repel because the two have the same sign. So electric field is basically an imaginary field that a charge makes that could apply to additional charges if additional new charges are introduced to the field. So now, when we talk about how strong or weak the electric field is, what would be the standard? How can we say that an electric field is strong or weak? Now, it's easy if you think it this way. How can you say, let's say a baseball player, a batter, is a good batter or a bad batter? Well, you can estimate that by letting him hit the ball of a standard baseball pitcher. Now, you can't just give any random pitcher. You can't just make Ohtani throw to the batter because then the batter won't hit a single ball because simply the pitcher's too good. Also, you can't make him hit a ball thrown by an 8-year-old baseball player because 8-year-old baseball player's ball is going to be extremely easy to hit. Thus, the batter would look like he's extremely good. So you want to introduce a standard average pitcher, throw a ball to the batter and see how good the batter can actually hit. Same thing. If you want to estimate how strong an electric field is, you don't want to introduce a weird charge, but you want to introduce a standard charge or a unit charge. Thus, the electric field strength is literally the electric force that a unit charge would feel when it's introduced to the specific location on the field. Now, when you say unit charge, it's a point charge with a charge plus 1 coulomb. Now, so for example, if the question wants to know the electric field at this point, basically what the question is asking, what would be the electric force between the charge over here and an imaginary plus 1 coulomb standard charge if that's introduced to this point? How much force would be induced between the two charges if this standard plus 1 coulomb charge is introduced at this point? That is basically what the electric field strength is asking. Which means the formula for electric field would be same as the formula of the electric force, which is KQ1, Q2 over R squared. But what you have to remember is that Q2, or the second charge, the charge of the second charge, would be plus 1 coulomb, because the second charge is always going to be the unit charge, the standard charge. Thus, its charge would be plus 1 coulomb. So instead of writing KQ1, Q2, you can simply write K times Q1 times 1, which is literally just K times Q1 over R squared. Now, of course, I mentioned how the second charge is always a plus 1 coulomb charge, but the order doesn't matter. Whether it's the first charge, that's plus 1 coulomb, or it's the second charge, that doesn't matter. It's only for simplicity's sake. I'm just explaining that the second charge is the standard charge that you're looking at. And the first charge, or the Q1, would be literally the charge in the middle that's actually making this electric field, the actual cause of this electric field. Now, I forgot to mention this. I forgot to mention the units of every variables you have here. So for force, you would obviously use Newton. For the distance, you use meters. Now, this will be very tricky because think about it. Charges are, after all, really weak. They're not strong enough. Think about it. Think about a point charge. Think about just one unit charge. It's going to be extremely weak. Thus, if they put them apart a few meters away, practically, there won't be any force induced between the two. That is why in most situations, the questions give nanometers, which is 10 to the power of 9 meters. However, always remember, even if the question gives you nanometers, you have to convert it into meters and then plug into this formula. Finally, Q1 and Q2, the charge. The unit of the charge is Coulomb. And I'm pretty sure this is something new to you. But well, that's how it is. And it's not even that hard to memorize because it's C for Coulomb, and Coulomb is literally the name of this force, Coulomb force or Coulomb's law. So it's going to be painfully easy to memorize. Now let's move on. Electric potential. Now, again, electric potential is a concept that might be hard for people new to E&M to understand because simply we never use it in real life. We never use it in mechanics. Now, the definition of electric potential is basically the work required to drag out a unit charge from a given location on the electric field. So for example, you have a unit charge over here. Then the electric potential at this point is basically the amount of work that you have to do in order to drag out this one unit charge out infinitely further away from this center, this charge in the middle that causes the electric field, so that you don't feel any electric field anymore. So it's similar to gravity. You want to pull out the object far away enough so that the object does not feel gravity from the planet. You want to pull out far away enough into the space so that there is no gravity present. So the electric potential is, again, the amount of work required in order to drag out a unit charge if it's placed on that location on the electric field to somewhere infinitely far away so that the charge does not feel the electric field or the electric force anymore from this center charge, the charge that's making this electric field. Now, the formula for this, and by the way, electric potential, you use the alphabet V, and the formula for this is KQ over R. Now, I don't really have a way to help you memorize this because unlike the above two, which are related, the above two formulas are in fact related. They're like literally the same formula, except in the second one for the electric field, you just plug in 1 inside one of the Q's because one of the Q's, it should be a unit charge and thus have a charge of +1 Coulomb. But for this formula, I can't really find a good relationship. So that's unfortunate, but anyways, you can just memorize it. Anyways, but the formula is not that different from all the other formulas, so it's not going to be really hard to memorize. Again, V equals to KQ over R. Now let's talk about electric potential energy. Now, what's interesting about electric potential energy is that electric potential energy is, now we have to think in this way. I've explained this in one of my AP Physics 1 video, but what is the definition of work? Well, you might say it's force times distance, but another definition of work can be the change in energy. Think about it. If you do some work, then you'll lose energy. Thus, the amount of work you do should be equal to the amount of energy that decreased. Now, electric potential energy, electric potential, and electric potential is the work. Thus, the amount of work that you do, the amount of electric potential required would be equal to the change in electric potential energy. However, the difference is that electric potential energy is not for just unit charge. It's not a characteristic of a specific location on the field, but it's a characteristic of a pair of charges, pair of two charges. Thus, for electric potential energy, it's the amount of work that you have to do to drag out not a unit charge, but a charge that can have, for example, be 2 coulombs, be -4 coulombs, or whatever. A proper non-unit charge infinitely far away out of the electric field. Thus, the formula would be literally V equals to R over under KQ, but you would have to multiply another Q because now you're not just dragging out a point charge, but this time you're dragging out a charge that actually has a charge more than 1 Coulomb. Thus, you would have to multiply another Q, the charge of the charge that you're pulling out. That is why you get this formula for electric potential energy. Now, you have to keep in mind that when you say work required, it's very confusing because again, let's come back to this situation over here, the blue situation. Now, you have a positive charge that's causing the electric potential or electric field. And on this point, you're putting a unit charge, which has a charge of +1 coulomb. This one's also positive. Now, positive and positive charge would induce a repelling force, meaning that this +1 coulomb charge is going to move farther away, infinitely far away out of the electric field, regardless. Even if you don't do work, still this charge will go out of the electric field because there is a repelling force present. Now, in this situation, some people might think the work required is 0. However, it's not. It would be minus kq over r. Why? It's because basically it's not that you don't have to apply work to this point charge to drag this out of the electric field, but in fact, you receive work from this charge that's moving by itself. Even though you didn't do anything, this charge is just self-motivated and it's moving, it's doing work by itself. Thus, this point charge is not getting applied work, but it itself is doing work. Thus, the work that you have to give in order to drag this point charge out would be, in fact, negative. Thus, it will be negative kq over r. Now, you don't have to memorize two formulas. You don't have to memorize plus kq over r and negative kq over r, but just know this, that the magnitude of work is kq over r, and you can just decide decide the negative or the positive sign, depending on whether the two charges, the unit charge and the center charge, have the same, are the same charge, like positive, both positive, or are they different? If they're different, then of course you would have to apply work and you would have to drag it out using your force. Thus, you would have to apply work. Whereas if they have the same sign charge, then it will be self-motivated. It would work by itself in order to get out of the electric field. Thus, you would in fact be received work. Now, you won't have to apply work to the point charge. Thus, the work that you have to apply would be negative. Just keep that in mind. Finally, these are some formulas that can help your mind processing. Now, if you look at the formula for F was kq1 q2 over r squared. E was kq1 kq1 over r squared. Thus, obviously, you can make the formula k equals to E times Q, because if you multiply one more Q to E, then that becomes F. Same thing for V and E. V is equal to K Q1 R, and E is equal to K Q1 R squared. Thus, if you multiply R to E, then you would get the formula KQ1 over R, which is equal to V. And finally, U equals to VQ. This also works because the formula for U is KQ1 Q2 R, and the formula for V is KQ1 R. So if you multiply one more Q to V, then of course you would receive U. That is why these three formulas work, which means if the question gives you one of the three, either F, E, or U, or V, one of the four, then you can use those information and additional information like R or Q in order to calculate the other ones as well. Now, finally, there might be some questions that actually connect the mechanic part with this electrostatics. This is possible basically because if you think about F, let's think about F. F is force, and force can be made by Coulombs law. Now, of course, if force is made, that would accelerate your point charge, meaning that this electrostatics can also be connected to mechanics. But when that happens, you don't have to worry. The only two things out of four that we learned, F, E, U, and V, the things that can be actually connected to mechanics is only U and F, because F is force and U is energy, and energy and force are the two things that also exist in mechanics unit. So simply what you would have to do is just use force to calculate F equals to ma, the acceleration, how the charges actually get accelerated, or use energy, U, and use the conservation of energy to figure out what would be the kinematic energy induced by the electric potential energy, or something like that. So that's not going to be very hard. If you want more specific example, I'll also record a video about just solving questions, solving practice problems. And in those problems, of course, there would be such questions, so you don't have to worry about that. So that's it. That's the concept part of the electrostatics unit, the first lesson. So thank you for watching this video, and please don't forget to have a great day.